Hello. Hi, everyone. Good afternoon, good morning, depending where you are. Or night. Don't know yet. Welcome. We are going to do something a little bit different today and do some research in the Go compiler and the runtime system. I'm not exactly sure we need to look at the compiler just yet, maybe later, but at least we're going to look at the Go runtime and Go routines and the Go routine scheduler. There are a couple of things that in the CockroachDB project we have found was problematic, and so we actually are doing a lot of work to try to work around limitations in Go with the ideas that in order to enable maximum reuse of CockroachDB source code in other Go projects, we don't want to depend on custom changes to the Go toolchain. But for the CockroachDB project product, that is running on servers, where we control the build and how it's produced eventually, and how it is run and how it is supported, we have found that there are actually a couple of problems that we really can't work around by just looking at Go libraries and so on. And so it's not exactly sure how we're going to achieve this yet, but it is likely that we do need to look into custom patches to the Go runtime. There are a lot of tricky questions that come with it, that in terms of productization. Again, if we want to let the community use CockroachDB without our custom changes, that will mean that we will need some way to make it work even without our Go custom changes. That's like there should be fallbacks or something like this. But this is not the question for today. Today we're going to explore the source code of the Go runtime, which I do not know very well yet. We're going to do this from first principles and try to figure out which are the control points inside the Go runtime that we can look at to achieve some of the goals here. I'm going to start with a simple problem that we have and try to customize this as a way to get acquainted to the process. And then after I do this, we are going to look into some other things that are more inside the Go runtime and a bit possibly involve a bit more work or different kind of work, and see how far we get with that. And because this is kind of a research project, it's not clear ahead of time what we are going to find at the end. So the general idea that we are aiming for, at least today, is to see how far we can get with the idea of exposing the state inside Go routines, that is inside currently the Go scheduler, to applications written in Go. So the Go developers really are allergic to the idea of exposing data from Go routines to applications, but for an application that is so sensitive to performance of the scale of CockroachDB, that is not really an argument, and so we are going to try to do something about that. So what we get today going to be a kind of an open question, but we are going to try a few things and see what we get from that. So here is a text editor. Oh, I see your message, null bitmap. Hi. That is large ancient. I actually don't know this emoji. We'll see. All right, so today my code editor is configured to a clone of the Go repository, and we are working on the 1.16 branch of the Go compiler. As it goes with changes to a toolchain, we have to be very careful about which version we're modifying, and also if this project gets anywhere successful, then there will be a very important question to be asked about how to maintain those changes over time and ensure they don't conflict with the other development from the Go team. So we're not going to cover those aspects today, but supposing that we do get somewhere and we find some changes that are worth keeping, there will be some kind of engineering task separately to package those changes in a way that we can easily carry forward as the Go team moves forward with the Go project. So let's see. So the number one thing that we were looking at is a little property of the Go runtime, which is that it writes any error that it encounters into the file descriptor 2, and that is fixed. So if you look at the runtime system, you will see that there is a low-level printing facility in the print.go file. And that is used for reporting panic messages and other internal errors in the Go runtime. And that code writes directly to the file descriptor 2, which is standard error on Unix, and doesn't use a standard library. And so we have a question, which is, okay, how does this get written? So we see this write error, and we see here write 2. And here we are. So this write error seems to be a common function used throughout a lot of other files. So let's see what Android does, because Android is different, obviously. So we see here that there is also a write 2 here, and it also copies probably the data to some other file descriptor. So we have here a write 2. So I'm going to now check whether we have write to only in this. Now actually we have a couple of places, but we don't have so many of them. And so what we can do now is a custom override of the file descriptor to which all these errors write to. And so we are going to create a new file, and that is stdr override.go. We need to be a bit more careful here. The cockroach TP authors. Probably we do need a copyright adjoint from the Go authors, and we do need to keep the copyright lines. That's actually something that's kind of a discussion that needs to happen later. How do we deal with the fact that there are going to be multiple maintainers, both the Cockroach DB team and also the Go team? That's going to be kind of an interesting question. So this is going to be a file descriptor. So what does a write? It takes a uint ptr. All right, so var stdrft uint ptr. Now let's see if the Golang supports uint ptr atomics. If it doesn't, we will probably need to look at a different data type. That is, so store. Yes, we do. Excellent. All right. It's 2. And then we are going to export a function. Set external RFD. Changes the file descriptor used to emit panic messages and other internal errors by the Go runtime. I hope that I can import atomic from here. Yeah. We'll see. Fingers crossed. This is valid. And so we are going to do atomic store untptr. All right. And then for internal use throughout the remainder of the Go runtime. I think. We need to do this because the file descriptor might be used concurrently from multiple places. So sarcastic alien beginner questions where's the symbol that looks like the lambda symbol before the function name. That is in fact a lambda symbol, and that is my editor's alias for the func keyword in Go. I hope this answers the question. All right, and now we are going to change this. Cool. And Darwin. All right. All right. All right. It's plan 9. I wonder how many people are still using plan 9. All right. Stubs. All right, we do need to create a branch, and that is going to be CRDB fixes. Let's call it CRDB fixes. All right. So I'm making here a fingers crossed call that I can use the atomic package from here. It's actually sync atomic. And that the build of the Go system is going to let me do this. Fingers crossed. Doesn't look like it. So I think that the problem we have here is that the atomic package in the sync subpackage might not be available in the context of the runtime system, because the runtime system comes first, and so it's possible that we don't have access, but we have an internal atomic package here. And so it would be interesting to see if the atomics package has a option, and it seems to have. All right. So runtime internal atomic, and that is small letters. Let's try that. Okay, I will admit ignorance. I actually do not know how to build a Go runtime with custom patches. And because I don't know this, we will have to read a little bit of the documentation. So there is a make file here. Let's just make.dist. Maybe I can do go tool dist. Test. Bootstrap. I'm going to decompose the script here and see what it says. Let's make.bash. Oh, I thank you, Rail, for suggesting to build it first, but I did do this before, and that actually was working already. So the errors that I see, oh, there we go. The errors that I'm seeing here is new, is because of my change, and that needs to be a uint bit here. Yeah, that looks better. All right. All right. So this change, for what it's worth, is ready to go. And I also learned how to run the build. And so we are going to double check whether we are done with this. By checking if there are no other remaining users of the file descriptor 2. So grep right of 2 here. Seems to be fine. Who thought it would be a good idea to write to the file descriptor 2 without any chance to change it? Oh well. Oh well. So there is, of course, a perhaps desire to customize whether this writes to file descriptor directly or whether we could use a Go os.file. But inside the runtime system, typically we don't have access to the other facilities of the Go library, standard library, because the runtime needs to work without the standard library. And so, unfortunately, we can't use all these abstractions. Why is it important to write to a different file descriptor? Well, in CockroachDB, we use the standard error to report progress on the server initialization, the server lifecycle, and so on. But we want all the error messages that happen inside the program due to, for example, a bug in our programming or some other application problem that caused an error inside the Go runtime to go to a log file on the file system. And today, we are not able to redirect all those panic writes to a log file without also redirecting all the standard error writes. And that is silly, because what we really want is to have the runtime errors to one file, the standard error writes for logging and other purposes to the real standard error. And so that's why we want to separate them. And that is today not possible until this API becomes available. And so we are going to explain this now here. Make it possible for apps to customize, say, FD for runtime errors. All right. For applications like CockroachDB that wish to peruse ctdr for logging, but a file another file for so what do we want to say here? To capture crash informations, panics, check faults, etc. We want a way to override the file descriptor used internally by the runtime. This patch achieves this. You are welcome. Off we go. So that was a good exercise. Now we are going to go forward and try to understand a little bit what's happening with Go routines. And so for this, there is a README file, actually. I remember. So what is this README file? Hacking. Yeah, there we go. All right, so let's reminisce these ideas. So a G is a Go routine. And then we have G objects, an M is an OS thread that executes user code. And then we have a P, which is the resources required to execute Go code, which is scheduler, memory allocators, and so on. So we have Go maxproc Ps, but there might be more M's than P's. So what is happening is the scheduler selects a G, puts it on an M, and selects a P to run it. And it's possible for an M to spend and then relinquishes P to another M. So in other words, we can have more threads, OS threads, than there are processors. So P are like processors in hardware. M's are like OS threads that share physical processors, and G's are the cooperative concurrency units in Go. So what we do not have today inside Go is an API to inspect which P a current Go routine is on, and which M we are working in, and which G we are working in. And so we want an API to expose this data. Now, that being said, of course, everything I just said, we need to qualify this. Is there maybe some information in the runtime system? We need to briefly look at this. And then we have runtime debug as well. So let's see if so we have a couple of environment variables. And let's see here in this API. So we have Go maxproc, Go scad. So Go scad quickly yields a processor. We don't know exactly what this does, but whatever. So num CPU probably returns the numbers of P's. We're going to confirm that later. And then start trace, stop trace. Right? Yeah, so none of this actually exposes the Go routine information. So we're going to look into this. Now there is a suspend, lock and unlock OS thread. All right, so this makes it possible to pin a Go routine to one thread. Okay. Unlock OS thread goes with it. Okay, so there is some form of pinning of a Go routine to an OS thread, but it doesn't give us a way to pin an OS thread to a processor. So that's going to be interesting. So let's do some introspection API to expose the G's, the M's, and the P's to applications who actually know better than the programmers and the Go developers. So where are those things defined? So scheduler, no, maybe. So where do we have? We don't know exactly where to look, but at the moment we will find one reference to an M or a P or a G somewhere. We will probably be able to immediately go and find the other things. All right. So. Proc. I like proc. I like proc processing. Cool. Let's do some reverse engineering here. So we are indeed in the right place. The coroutine scheduler. Worker thread, parking, and unparking. So even without looking at this doc from basic computer architecture concepts, that is when the M's are going to arrive on a processor and do work versus not. So it's some the explanation about what gets into a P, what gets into an M. Okay, and here we are. So we have M's and we have G's, and then we'll probably have P's somewhere else. But okay. Anyway, so let's talk about the G's. So that's great. So the G is probably a predefined inside the Go runtime a primitive, and so we have a couple of things, but the things that we are going to extract already is the Go ID and probably maybe other things. Ancestors. That's only with traceback, so we're not going to make it available as a default. We have traceback context. Might not. And then per GC state. So, oh, interesting. This is credit. Interesting. So actually, it's fascinating because we always assume in CockroachDBs that Go routines don't really have a special status in the GC, but in fact they do. Oh well. What else can we extract that is valuable? Maybe the size of the stack today? Do we have size of the stack somewhere low and high? Well, that sounds promising. All right. proc-api.go. Yay. We are going to copy this and then say get let's name our functions well. So G get stack size. Get G stack size. Not that we need it. Retrieve approximation of the current Go routines stack size. Oh, come on. I think that's okay. And retrieves the Go routine. And that is an int64. Off we go. What else? Ah, interesting. So where is this being set? Panic on fault. Set panic and fault. Interesting. Or is that being used? Look, it is. Set panic and fault. Oh, in fact. Oh, that is cool. That is cool. So actually we do want probably to read about this debug package, because it seems to be interesting things inside. Set panic and faults. I like that. I really like that. I wonder what the default is though. I wonder if that, so how that is being set. So that's the override. That is go exit, so that is at the end. Then this. So panic and fault is not being initialized by default, unless I mean, so nothing sets it. So by default, it's not set. So actually, by default, a thread is enabled to catch those panics. Well, that is a bummer. We probably want to override the default. All right. So where are G's allocated? Of course, there will be plenty of those. Let's see. Probably here. We are going to... Oh, there are all G's. Oh my gosh, there are all G's. All G's are being... Oh, that is cool. So we do have a registry of all Go routines. That is fancy. We'll see about that later. Anyway. Where are... Okay, so there is a new G. Okay. New proc. That seems like what the Go compiler does. New G mag. Doesn't look like it copies the flags from the current one. All right. Cool. Okay, so what we are learning here is that the flag for panic on writes is not being initialized by default. So let's see if we have a atomic interface for booleans. Doesn't look like we do, huh? Just uint. Do we have more? We just have load uint, store uint. Doesn't even have store uint. Oh my gosh. But there is a load 64. Atomic, AMD. Oh, here's they are. Alright. So load and store. I like this. Oh, there is even a store 8 and load 8, maybe? We don't have a load 8. So let's do load and store. Store. Store, yeah. So we do have load and store, so we can remove all this and then go to our API file. And then set default panic on... What was the name again of this fault? Set the default value of the panic on fault that is otherwise customized with debug. Okay. So var default panic on fault in 32 is 0. And then we are going to do func set panic bool. Is it panic? Enabled bool. And then we have this uint, sorry, in 32 of if not enabled, v0, and then atomic dot store of default panic and faults as a value. And then we import the atomics. Are you modifying the standard library to be able to access these unexported functions? That is a question. Yes, this is exactly what we are doing today. This is what we are doing today. And now let's see. And we are going to do debug panic stubs.go. Oh, in fact, very interesting. All right, so debug.s garbage. Okay. We probably need a cas here. Stubs. Cas. Exchange. Exchange. Cool. So that needs to be a uint. And so we are going to be, so it's going to be a uint. And then all right. All right. Cool. Let's try building this. Does that mean CockroachDB is compiled with a modified standard library? No, it does not mean that. Today's program is to do some research to see what is possible to add to the Go runtime, and then explain this to the CockroachDB team members. And depending on circumstances, we are going to use this in CockroachDB. It's not the case yet. And if/when this happens, there will be a fallback so that you can still build CockroachDB without the changes. Anyways, the changes will be exported so everyone can look into it and understand what's been done. But we are creating here an environment where we can do proper systems research on resource management and error handling in CockroachDB without being subject to the decisions of the Go developer team. And that is for our own research purposes to see how to make the CockroachDB project better. And it doesn't change anything to the fact that people who wish to not use our changes will still be able to do so. You are welcome. All right, so let's try to build this. What does it say? Cool. Oh, my computer is unhappy. Very slow now. Yeah, generally busy. Computer is busy. But it did build. All right. So that seems to be fine, but there is something going on with the text editor. My poor Emacs has decided that it's not happy anymore. 64, yeah, well, unfortunately with the Go programming language server, memory usage is a problem, and so more memory means it can fit all the source code in memory so that you don't need to access the disk. All right. So that is something that we probably will need to rename all those functions later on to make it clearer, even clearer, that they are custom. Maybe we even need a separate package. We'll see. Type G? No. G. So this is a G. Now the M. And then the P. Do M's have identifiers? I don't know yet. We are going to find out. Proc ID. That seems interesting. So what is a TID? It's proc ID, okay. Oh, it's the OS thread ID. It looks like it. That seems interesting. All right, so why is it only set on FreeBSD? So this is a way to send a thread. Yeah, okay, I like that. So it is the internal OS thread ID. That is actually pretty cool. But we are going to check if this is not set in assembly. Yeah, it looks like it, huh? Yeah. Get TID. Yeah, there we go. Okay, the thread ID. Proc ID is the OS thread ID. All right. Get thread ID. And that is UN64. retrieves the was level thread ID, which can be used to set scheduling policies or retrieve CPU usage statistics. And so off we go. Problem solved. Cool. What else do we have? And then there is a P. We're going to look at the P in a second. Okay. All right. What else do we have? Do those M's have identifiers of some kind? Maybe the G0 has something. So what is a G0 about? So every M has a system stack associated as the G0 stack because it's implemented as a stub G. And on Unix platforms, a signal stack. All right. Oh, okay. Interesting. Okay, so actually, it is good that I'm reading this documentation. It says that we need to be careful about this. Sketchy.m.curchy. All right. Curchy ID. Okay. Cool. Well, in fact, that might be good enough. Okay, yeah, let's do this. Because the M is shared between G0 and the current Go routine. All right. So we have here a couple of things we will need to do about Go routines a bit later. So, okay. Is there anything else that's happening with a P? So, with an M, sorry. Alloc M. So let's see. So there is a free list. And there's a comment in it. Then there's G0 allocated. And that doesn't really allocate a integer ID, so okay. So M's don't seem to have a acquire M. Why do we need acquire and release on those things? We'll see. If so, we might need to determine if we need acquire M and release M to observe the proc ID. So erase detector will tell us if we need to. All right. And we probably need that here too. Oh yeah, and we forgot to change the panic unfold. In this file, let's see, where is this being set? Our debug, set panic unfold. There's a new one, I see. So it doesn't change. Okay. New G. Mal G. So that's where the G's are being initialized. And so we are going to say here go crush db tweak. Why do we need this? Is to ensure that diffs later, when we apply the same patch into new versions, the diff will apply cleanly. Panic unfold, and that is going to be the thing we have here. All right. All right. Color PC. There is something that we will need to do at some point. Here's a system go routine. What is this? Must be omitted in stack dumps and the log detector. Oh, interesting. So the go routines from the go runtime itself are not included in stack dumps. I did not know this. The more you know, the more you know. All right. So let's try to build those changes we have so far. So let's see what those changes really are. I'm going to constrain this. I don't want to use all the cores. Oh, of course, we forgot. We wanted to extract the P's. That's P. Come on. Oh. Oh. All right. Oh, look at these. They're identifiers. Oh, there are statistics for each P. Oh. Oh, that is awesome. Where is this included? So we will look into per go routine and per task statistics a bit later. But it's good that there are already some statistics. That's actually that's good, I guess. So let's see how that ID is being allocated in it. All right, so there are here some. Okay, so where is this call from? Here. Initialize no new piece. Oh, and there are eyes old. Let's go max procs. So they are destroyed. And then they're in it. Oh, P of I. Oh. Oh. That is so cool. All right, so that's cool. So we have a guarantee that the eyes are the PIDs are in the order. Oh, that is so cool. Get PID retrieves the P virtual CPU ID of the current Go routine. And it's an int32, isn't it? ID? Yeah, it is. ID. Off we go. Oh, yeah. PTR. There we go. Cool. Cool, cool, cool. All right. So that is actually... we need to have a API we will need to rename those things a bit later, probably, to get some clarity about what's going on. All right. These are by design set between, is it one and go .id proc.id. Where did we see that in it? It's going to be 0 and go max proc -1, I think. Right? Isn't this what it was telling me earlier? Ah. That is really cool. That is really cool. Be used to create data structures with CPU affinity. Note, because of preemption, there is no guarantee that the Go routine remains on the same P after the call to get P completes. All right. It's kind of funny because the pull mechanism inside the Go runtime also uses the some information about the C processor. So let's see. Oh! Oh, that is good. You can pin things. And then there is a pin slow. What is this pin slow happening here? Ah ha 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 ha. Let's go. Let's go. G to its B and disables preemption. The color is responsible for calling unpin. The GC is not running twin pin. Segment J. So how was this used again? Proc pin is a PID. And it returns the current the ID. B has the G has. Unpin. All right. I see. Does this build? It looks like it does. No, it doesn't. It does not. Why? Yep. Off we go. Okay, so we have pin, we have G's, we have M's, kind of, and yep. Note. Because of preemption, there is no guarantees. That's the current routine. remains on the same thread after call to this function completes. See bin and bin for details. All right. All right. All right. All right. All right. Mm-hmm. Okay. So we are going to commit this and say runtime new observability API for GPMs and go doc runtime. Is going to tell us oh, is it there? Nope. Okay, so that is go root is dot. Yep, here. All right, so that's interesting. So I'm going to say the doc.orig, doc.new. There we go. New runtime API endpoints. Right, what are we missing? This one. This one is from the previous commit, so we're going to ignore it. And then this one. And now we can remove this comment. Off we go. Cool. All right. Now, folk, it has been a bit more than 1 hour since we started. It's very important when you program to take breaks and move your body and hydrate. And so time has come for a break. We are going to resume in a few minutes, maybe quarter to the hour. So take a break, enjoy your times, and see you in a moment. All right, we are back. All right, so if we come back to our issue from the beginning. All right. We have covered those two first points. And what we want now is customizable per routine state and multi-routine task groups. So the task groups is the thing that I want to tackle next. I have been told by a coworker that there is something called pprof with labels that already get inherited across coroutines. And I don't know how that works, but I do want that behavior to exist across coroutines. So, I want to understand how pprof labels are inherited. And if it says to me that they are inherited, I want to understand how that is working. And depending on how it's done, then we can talk about how to do it for other things as well. So, runtime.go. Set prof label. Come on. All right. Labels. What does this do? I have no idea. All right. Profiler labels. So that's what does it. So there is native support inside the Go runtime. And now let's see how those are inherited. Coroutine profile with labels. Say the current Go routine. Label map inserted here. Okay, so that's something that retrieves them all. So at exit, we remove the labels. And that's where we copy them. Oh, you know what? This looks like this can be inherited. Yeah. All right. So we need this and then proc.api. Say flag is inherited to children Go routines. The default value is used for top level Go routines that are started during the init process or as runtime. All right, so that we need to change and explain this here. So that is actually from the previous one, and Go routine. Oh. Huh. That belongs here. And we do want this to be documented in here. Oops. Documentation. Off we go. Cool? Yes? Alright. Alright. So, labels. We were looking at this, and we see that the labels are inherited. Are there other things that get inherited in this file, actually? That is the only thing that gets inherited, apparently. Well... labels. Labels. As a profiler labels the only place where this is being stored. CPU profile. It's not too bad. So there are two things we probably want. We want to attach arbitrary additional information from the application level, but we also probably want to have a few things inside the Go runtime inherited through Go routines and less overridden. So what we are going to do is adding a couple of fields. One for task groups, where the additional library will be responsible for grouping the task group together, and another one to add metadata to a Go routine that is going to be shared with the Go runtime, and then there is going to be metadata for application level things. All right. So what do we do about this? I want to be honest. I'm getting a headache. There are too many opportunities here. We are going to add a task ID, task ID. Yeah, we're going to do this in a similar way. Yes, runtime 2. Right? $64. Inherited Go routine group ID. typically set from say task group root's own go routine ID. Via set go routine group ID get GID. All right. Then we go here and then we say new g dot group ID is new g dot go ID. Is the ID already allocated by this time? Probably that is coming later. Yeah, it's here. That is here. Yeah, let's move this code below. So we are first going to move this code to here. Here. Yeah, so we need to amend our previous commit with this. And now we can work on this one. All right. That sounds about right. And that will give us a way to associate an entire group of Go routines together with other metadata that is defined application level. So each application can do its own thing, but of course, we need to add this to our API. Get Go routine group ID retrieves the task groups ID. This is the current, same as the parent Go routines group ID. Top level Go routine are assigned their own ID as group ID. Go routine. Okay. Is inherited. Okay. Set the current Go routines task group idea. This value is inherited to children Go routines. Okay. All right. That is going to make already a huge change in usability. I wonder. So these Go IDs are. I wonder if there is a way to associate data, task level data into Go runtime. That's a bit efficient. We probably will need to do this by adding P level data the same way that this is done here. Yeah, what we're trying to find here is a way. So the issue we have is the following. If we want to associate state inside the Go runtime efficiently to task IDs as like a struct or something like this, we can certainly inherit this. Like if it's provided by the application is responsible for allocating these task structs. But in reality, what we have is that we probably want to have per task ID groups of runtime managed statistics, like things that are not managed by the client app, but are managed inside the runtime system. And that is a concept that doesn't exist yet in the Go runtime system. And so what we are going to do here is to introduce these concepts by having a struct that looks like a G, but it's not really a G. It's going to be probably a T, which is something that doesn't exist yet. And it's going to be numbered after the G's because the T's only start to exist on G's. Which reminds me... yeah, that's going to be fine. And so we will need a way to allocate them efficiently, and that means that probably, yeah. Let's say maybe we don't want that to be set by default. There's a lot of complexities that would go into adding a facility for task groups inside the runtime, like allocating them. But what we can do so is to define a stack group, a task group struct in the Go runtime. And then have a way to attach them to Go routines. Yeah, that sounds fine. And then there will be state in a task group that is not exposed to client applications. All right, so what do we want in a task group inside the runtime system? If it's defined, yeah, okay, so we'll see. So what we're going to do is add another... do we already have committed? Oh, no, we haven't. here, here. Off we go. So, runtime. New inheritable task group ID. Task group ID is analogous to, say, Go routine ID, but is inheritable. Inherited. Children Go routines. And now we are going to copy paste the docstring from this and here into commit message. All right. Cool. So that is now addressed. What am I missing? A way to attach these task IDs. Maybe we can start trying this out already. Now, what we really want is a way to associate stats. We want to have a way to associate state and stats to task IDs. Yeah, let's create a task group.go here, and then we are going to have a type T we're probably going to have allocation pool, a free list, probably. Type P. Sorry, is this one? I'm not going to look into this. So, TBD. And now we are going to say func. Do we want to export this type or not? Probably not, huh? How do we identify, say, a task ID as a task struct if not by an identifier? With the uint.ptr, I suppose. Create task. I don't recall how uint.ptr works in pointer. But not back to pointer. Yeah, that's not really great, huh? Yeah, let's. Yeah. I must say I'm not super comfortable with this. We need to look at this a bit later. So we're going to have task ID. It's going to be an int 64. Right? And then we're going to have a tease. D. And then we're going to have last. All right. Great. Group. Do we want to have that? Yeah, probably we do. Let's not expose the IDs and let's not keep some. Oh yeah, I like this. I like this. Actually, I don't need to look at this at all. All right. So get g and your g dot task group. There we go. This is inherited. Right. And then yeah, I suppose that will be sufficient for now. Cool. Group ctx. And what do we do about this? We probably need to log this. Do we want to log this? I don't remember if we need to log this. Log.go. Log init. No. Where? Here. This is a release M. Or logs. B. I suppose we need acquire yeah, so we are probably going to have our to do here if we need require release here, right? Set. Cool. And so what do we have in a task group? We are going to have a couple of things related to scheduling. In particular, the scheduling ticks. Scheduler calls. Inherit time. Time slices. So there are time slices. That is great. I like wait scenes. I really would like to see something like keeping track of the waiting times. So yeah, so those things are getting dumped. Wait scenes. So that is when a go routine gets suspended, I suppose. Oh no, that's during the GC. So where is the wait scenes being set? Oh, maybe... So apparently the blocking is only happening during GCs? Yeah, maybe. Maybe. What we really want here is to have some information about how much time was spent ticking, maybe. Let's see, what is this information? Presented on every runtime. Execute. Okay. All right. Retrieves the number of scheduler ticks for all go routines in the current task group. Panics if no task group was defined. Maybe. Returns 0. No. All right. Now we are able to retrieve the number of scheduler ticks in a Go routine. Right. All right. Runtime. New task group internal state in the runtime. This commit adds support for task group level state inside the Go runtime. Separate orthogonal to the task logical. Task group ID introduce in the previous commit. This is envisioned to set oh, I can see something going on. Oh, this is good. Right. To contain state that the runtime needs to know about. The first expose metrics collected by task group is the number of scheduler ticks, which gives estimate of CPU usage for a task group. Let's copy the API here. Cool. But there is something that we probably want, and that is a default task group. Default task group. For top level Go routines. Okay. Yep. Task groups. All right. All right, let's try to build this. Make was a mistake. Default task group. Setx. Seems to be fine. And I think that this will be good enough for today. In fact, so we don't have that yet. We have this. So we have this. There's this. We don't have that yet. We don't have that yet. All right. All right, and we do need to add something to explain. Top level Go routines set. Oh, come on. Top level Go routines that have not been set a task group. Use a global default task group. Share. All right. And we are going to push this for today. And for today's stream, that is more or less going to be some preliminary experiments here, and we're going to point to the new branch here. In this one. Cool. All right. We probably want to include the API change in this first commit. Let's do this. So what was the initial patch that we worked with? This one. Let's see. And edit first commit message. All right. Proc API. No. Error override. This one. Okay. All right. All right. All right. And I think this will be sufficient. Yeah, looks fine. Looks fine. Okay, cool. All right, so to summarize. We started today with this exercise to add this API to the Go runtime to override the file descriptor used to dump Go panics and other internal errors to the Go runtime. Sorry, that light is a bit dark. Let me turn this on. Go. Then, after we went through this little exercise, we added a way to inspect the properties of the current Go routines, virtual processors, and OS threads. Then we added logical thread group ID, task group IDs to Go routines that applications like CourseDB can use to associate application level state to task groups. And then we have separately an internal runtime, Go runtime task group struct that is going to collect runtime level statistics about task groups, and that is also set separately, but here we don't control, we don't set the group ID arbitrarily because it needs to be a struct. And so the only thing that's possible is to create a task group for the current Go routine that's fresh, and then we can retrieve its properties. We might need APIs to inspect all the task groups that are currently defined, but that is not yet a need, and so we are going to come back to this later. Well, for today that's sufficient. The next iteration of this work, either in the live stream or off stream, will be to create an example application that demonstrates those APIs and the benefits. And there will be some work needed as well to make the custom changes to the Go runtime here portable in a way that it's possible to build client apps that depend on this API even without the customized Go runtime. We'll see. We'll see. In any case, thank you. Thank you for watching. Thank you for joining today. This was a little bit of research also for me to learn about the Go scheduler and the Go routine struct and so on. There will be more experiments needed to understand everything we need, but that got us started on a path, and so hopefully you enjoy the ride, and we will go further from there next time. Thank you for joining, and thank you for being here. Have a good day.